Hello, everyone, and thank you for joining us today. My name is Fabiana Di Gianvincenzo. I am a postdoc researcher at the University of Ljubljana, and I am one of the organizers of this new lecture series, Current Topics in Heritage Science, which is part of the E-RIHS Academy series. The other organizers, whom you can see on your screen right now, are Tiasha Riavets and Hassan Ebeid, also from University of Ljubljana, and Antonina Chaban, Diego Quintero Balbas, and Moira Bertasa from the National Institute of Optics in the Center for National Research in Florence. As part of the lecture series, 10 excellent speakers will present the research, focusing on fundamental aspects of heritage science, such as techniques and methodologies, but also materials used in cultural heritage and discussion of technical and ethical issues, such as the ethics behind planning sampling procedures. The lectures are targeted at emerging professionals, such as students and young researchers, but also advanced conservators, curators, restorers, and other cultural heritage stakeholders. The primary aim of each lecture will be to give the audience all the tools to understand the topic, independently learn more about it, and eventually be able to apply it to their own work and research. We hope you will join us in all the future lectures as well. You can find more details about the lecture series and the future lectures on the E-RIHS website. All the lectures are recorded and will be available on the E-RIHS YouTube channel after the lecture. Our speaker today, kicking off the lecture series, is Professor Katrien Koene. Professor Koene is a chemist by background. She is currently head of science at the Rijksmuseum in Amsterdam and professor by special appointment of molecular spectroscopy at the University of Amsterdam in the Netherlands. She is specialized in chemical processes in heterogeneous complex paint materials. Today, she will be presenting a lecture titled From Model to Painting, Added Values and Limitations of Reconstruction and Model-Based Research. You can ask questions also during the presentation using the Q&A function, and your questions will be asked at the end of the lecture. Thank you, everyone, again. Katrien, the floor is yours.
Thank you, Fabiana. Thank you so much for your kind introduction and inviting me to be the first speaker of this fabulous series. I'm very honored to speak to you today, and I will do my best to give you an informative and engaging lecture on model systems in the next 30 minutes. The lecture is entitled From Models to Painting, Added Values and Limitation of Reconstruction and Model-Based Research. But to simplify things, I would phrase it as, what can we learn from model systems? Reconstructions play a vital role in conservation of cultural heritage research. I suspect most of you work with it or have read about it. In this lecture, I focus on oil paintings, but dilemmas, approaches, and limitations are definitely also relevant for other types of paintings and objects. In this lecture, I would focus on two core questions. One, why are we using models and reconstructions? And two, what are useful models and reconstructions? But first, let's dive deeper in the term models and reconstruction, as it can be very confusing. Depending on the dictionary you take, you get different descriptions. However, for me, a model is an extremely simplified version of a painting, having only a few key paint components. It makes it possible to investigate individual chemical and physical processes. While I see in reconstruction more complicated system, it may consist of several paint components and one or multiple layers. Although both terms are usually simplified versions, and reconstruction is closer to reality of a real painting than model systems. In the literature, there's a lot of overlap between these terms, so I hope to be a little bit consistent in this lecture, and I also can advise you to read one of these papers where this topic is also discussed. We just talked about the terminology as different complexities or, say, simplifications. There are different types of reconstruction and models you can select on your research question, depending on the research question you have. Here you see a row of different reconstruction and models where the complexity of a painting is increasingly stripped away. We have on the left side painterly reconstructions, toward the right individual pigment and oil, and computational mathematical models. At the end of the presentation, I will illustrate you to go a little bit deeper in what I mean with smart design models, but in this lecture, I will not focus on computational and mathematical models. So let's start. let's come back to the first question. Why are we using reconstructions? Well, I think you probably can have a lot of reasons why you would use reconstructions. But for heritage research, I've grouped them in 3 main research field topics. First of all, models and reconstructions help to give a better understanding in the artist's intention. Second, they help to better understand the change of the object. And last and not least, they help to better treat and preserve the object. I will go through them to give you an illustration for this. Let's start about the artist's intention. In this still life from the 17th century, you see the yellow rose in the center look nowadays quite dull and flat. And surprisingly, the matrix ref reveals the existence of the modeling in the arsenic map, as you can see in the middle. In this example, or this painting, we've investigated with all non-invasive imaging techniques, microscopic analysis, but also included historical recipes and sources to understand what the original intention was of the yellow rose. Based on all this information and results, we try to study it ourselves better. So we tried nuances in pigment composition, tried different build-up to understand how the Heem painted this beautiful flower. Other examples are, for instance, here, where they used reconstruction as a tool to investigate whether charcoal or blackstone has been taken as underdry material in 16th century panel painting, as this information is difficult to obtain from analysis only. Or in this example, where we made reconstruction from night watch, because Rembrandt used various variations of smalt and red containing paints in different ratios. But nowadays they all look quite dark and brownish. Based on paint reconstruction analysis, we are able to reconstruct the paints which show that they are much more nuanced and richer in tone. Then, how models and reconstruction help to understand the change of the object. As I mentioned, we cannot see the modeling of the flower today by eye, but we know it's there. So we were wondering, what is chemically happening here? What are the degradation pathways? So we really stripped it. We investigated the individual arsenic sulfide pigment, the ore pigment, as pigment powder, but also in paints, also with different substrates to see to the interaction and light age them. Similar approaches are also taken in more modern pigments, as you can see here, where cadmium reds are also exposed to light sources as pigment, but also in paint system to understand the photo degradation better. But not only degradation and photo degradation can be studied. Also in this example, I would like to highlight that also conservation treatment can be investigated. In this study, they are looking into the influence of wax resin lining, wax resin that's applied on the back of the canvas. And in this study with reconstructions is looking into how the wax resin impact the current appearance of a painting. And the last group I combined is to help better treat and preserve the painting. In this study, we use laser spectral imaging and varnish models with black paint to address the question, how long does it take if you use a solvent, how long it takes before it's penetrating to a varnish layer and coming into the paint. In this way, we studied different solvents, but also with the aim to better tweak our cleaning methods to have a safe, more controlled way of using solvent and solvent cleaning. Similar approaches, reconstructions here from research by the Tate are also used their cleaning methods to remove graffiti from a Rothko painting. So you don't test, of course, in a real painting, so you make mock-ups to really neutral and really nuance and search your conservation methods. And more to a mechanical point of view, you see here test systems, test reconstructions, where reconstructed paint on canvas are exposed to a relative humidity fluctuation, get a better idea of the response of the painting to relative humidity. I gave you a little bit insight in the rich information reconstruction and model system can give us. But let's shift to the second and important question. What are useful models and reconstructions to make? There are two topics I would like to into. What are the challenges? So why it's so complicated to make good models, and what are critical decisions to be made? First, the challenges. It's of course impossible to reproduce a painting, paint, or degradation effect exactly. And this is of course obvious, but actually it's really our biggest limitation when working with models and reconstructions. So our challenges, what are our challenges to study a 17th century painting with a model system? Well, here I listed 4 challenges, where the first one is regarding the original composition and production process. We often don't know the original materials or recipes of the paints. So there are a lot of unknowns in the starting process when the paint was made. And did they add, for instance, a little water or honey to grind the paint, or did they let it dry in the sun? That are indeed decisions or actions we don't know when we read the object or have the object. Secondly, it's good to realize that paint is very heterogeneous. And that's also what I would like to illustrate with this cross-section. And you see indeed it has multiple layers, but also the pigmentation is quite diverse. Local conditions around pigments can be a few micrometer away different. It can be more alkaline around, for instance, chalk particle, where it's more acidic around an ultramarine particle. You can see that at a micro and molecular level, a paint film itself is very high heterogeneous. And this is of course very difficult to steer and capture in reconstruction, but it's very good to be aware of when designing your reconstruction and model. The third topic, time, or the third challenge we have to bridge is time. I sometimes make the parallel with slow cooking for paintings, because chemical and physical processes are taking place sometimes in 100 years. So how do you squeeze them in a 3-month student project? And the fourth challenge, and not the least, I would like to highlight that you need to realize that the object you're looking at, or you had studied, undergone conservation treatment or past storage conditions. And that's what I would like to illustrate in this cartoon. We find often the degradation product palmerite on the surface of many paintings. And palmerite is a lead potassium sulfate product. And we have hypothesized that sulfate is an external source. And if you go back into history, you find that coal stoves are used to heat the galleries. And this coal is of course a great source for sulfur. And I think that is also what this cartoon is illustrating from the 19th century, where indeed you see the stove in the center of the gallery, and indeed the night watch hanging behind this on the wall. And then the critical decisions. So if you're going to prepare your sample, what are really critical decisions you have to take into consideration? Well, of course, you need to decide what materials do you use? How do you prepare your system? What are the best artificial aging conditions? And also, what do you want to do with them? What materials to use? Do you have materials do you want to have your materials historical accurate, or do you want to buy commercial ones? And do you press your linseeds yourself according to historical sources, or do you buy commercial available oil? And if you press them yourself, you need to be aware that the linseed flax are 21st century grown, so genetically probably not the same as they were grown in the 17th century. And with commercial available oils, it's very hard to know how they are prepared, treated, and refined. And one batch might not be the same as the other batch. And we often buy a bottle by us in the lab, what we use for years, so every reconstruction we use the same bottle. But it's very good to realize that from a chemical point of view, the oil in a bottle does not remain the same. The moment you open the lid, the oil is exposed to oxygen. And of course, it starts to polymerize. So the oil you're buying is probably not the same after a few months or a year. So depending on what the goal of your research is, you have to take this into account. So when you are focusing on mass spectrometry analysis, it's smart to keep your bottle, for instance, stored on the nitrogen. And I heard a tip from the colleagues of PISA who justified when they buy a bottle in small bottles from the beginning. So every reconstruction or every model, you take a new bottle. This is from the binder, all medium side. But let's shift to the pigments, where I illustrate here with a lead white. You see two backscatter electron images. And on the left, you see the backscatter images for Dutch stock 17th century lead white. This is from a Rembrandt painting. And on the right, you see a modern lead white. Well, it's clear that the particle size and the morphology are different between the 17th century and in this case, what was the 20th century. And the particle morphology and distribution affects the paint rheology, handling qualities, and visual properties of the paint. And modern lead white takes up twice as amount of linseed oil to achieve a workable paint compared to this Dutch stock lead white. So it's good to be aware that although you think you use lead white, it can be completely different than it is in your object. In the preparation of your reconstruction, there are a lot of minor decisions to be made. Did I use rainwater to rinse? And should I use rainwater? And to give you another example of that, we were making and purifying the blue ultramarine pigment from the lazurite stone. And one of the steps in this preparation is that you need to knead a dough ball underneath water to release the purest blue pigment that will be released in the water. And we used demineralized tap water with a controlled pH. It really took us the whole day to get a really low yield of ultramarine. But when we were kneading the dough in rainwater, with the same pH as the demineralized water, the job was done in an hour. And this is a very tricky one because you lose yourself in very small decisions to be made. And at a certain point, it can be counterproductive. So keep your research question in mind and realize also that it not always can be perfect. We spoke about original materials, or what materials to use. Now we shift to how to prepare your samples. Often you want to come with your reconstruction as close to reality, but is that really necessary for your question? If you're interested in, for instance, in the discoloration of a red lake, is it then important to recreate the entire buildup, including canvas, primer, underlayers, and then indeed the red lake containing layer? Isn't that not better to just have the pure red lake layer in oil directly on a substrate? But if you're interested in a degree of transparency in working properties, then it might be useful to recreate this multi-layer system, as the oil is absorbed by the ground and it affects the drying, and the whole layering system affects the final appearance of the paint. Then the type of substrate. If you go for a simple single layer, you mostly can use a glass slide or a plate, commercially prepared cardboard, as you can see here on the right, or a polyester film like Mainlex you see here in the left, which is also had the advantage that it's very flexible and an inert substrate. And then the grinding. Are you grinding by hand with a slab and a muller, or are you grinding with a machine? And to what degree do you grind? This might be determined if you need, for instance, small or larger portions. Only the longer you grind, the better the pigment is suspended in the oil. And that's important so you don't get a separation. And then the middle, the portions of the ingredients. What portions of ingredients are needed? This information can be gained from historical recipes, literature, analytical analysis, or just by trial and error. Do you wetten the pigment first to make a slurry and then add the oil, or do you add the oil directly to the pigment? And how much oil do you need to add? Well, always add the oils in person, grind the paint, and evaluate the working properties of the paint. Ideal handling property is not too runny and not too gritty, but really note that every pigment does not have a fixed portion. So it's really something you need to try. Then the application method. So you can apply paint by a brush or a palette knife, or by a drawdown bar, or by dropping on a glass slide, just a droplet. The benefit of a drawdown is that you can control the layer thickness, but be aware that oil paint always shrinks to a certain extent due to the oxidative drying of the oil. And lastly, if you make multi-layers, what time you need before another layer can be applied? It really depends on the type of pigment and dryer added. And in general, my advice is to collaborate with a technical art historian or a conservator who mostly have experience with hands-on paint reconstruction and historical recipe. And it's always good to have a dialogue there, what is best to use. Yeah, another decision you have to take is what is the best artificial or natural aging condition. And I really found this the most difficult topic to advise, because I think this deserves an entire lecture on its own. First of all, I would like to refer to the standard work by Feller, which is freely downloadable. And although it's from 1994, it provides a good outline. But be aware that since this publication, a lot of progress has been made and new insights have been obtained about the oil paint chemistry. I said it already, but I will say it again. It's important to realize that artificial aging can never mimic a neutral age paint film. And you can calculate the equivalent of the total artificial aging time to exhibition in museum conditions. However, an artificial aging paint will never be chemically and physically the same if you have the similar paint naturally aged for the same time frame. Because under light and thermal conditions, different chemical pathways and kinetics take place. But if you speak about artificial aging, I would like to separate this for two reasons. You can perform aging because you want to dry your paint film in your model to do, for instance, cleaning test, or you want to see the painterly effect, or the artificial aging is done just to understand the process. So if you want to understand the photo degradation of a pigment, then you also can do the artificial aging. In this lecture, I focus on the paint drying and aging. And these are factors how you can influence the aging of the oil. And you can use light aging, temperature, rate of humidity, or a combination of all these above. And if you dive into the literature, you see that every researcher use different light conditions, light exposure times, temperature. Therefore, it's not my aim in this lecture to give you the golden tip how you best can artificially age. I wish I could do that, but that's I think too complicated. But I prefer to give you more insight in the chemical process that can take place on the condition, so you can better make a judgment yourself. And at this moment, I need to give you a little bit of background about the chemistry for oil paint to understand how these conditions play a role and how you best can make a decision. Here you see the main component from oil and 3-acyl glycerol. And it's important to be aware, and I assume you all are, that oil and linseed oil have a chemical drying. So due to chemical reaction, they form a film forming. It has a glycerol backbone, and you have 3 fatty acids attached to it. And the double bonds, they are active in drying and making the crosslinks. And that's happening here. You see here the double bonds. You see that due to hydrogen abstraction, you get oxygen incorporated in your fatty acid chain. And this initiates really the auto-oxidation reactions. And that triggers a lot of peroxide bonds, and you get indeed your cross-linking and continuing. And this initiation auto-oxidation reaction is speed up by light, UV light, thermal or dryers, but photo UV having initiation by UV, that really speeds up the process extremely compared to thermal aging. Well, if this first initial auto-oxidation is started, so these radicals are produced, and then it goes on, and that is illustrated with this slide. And you see indeed you get cross-linked, you get all types of recombination. In the end, you end up with a 3-dimensional network, and hopefully also with a dried paint film. Well, we did in our group a lot of mathematical modeling on these drying process to understand a bit how can you describe a network. And one of the researchers found out that indeed in the first 10 days, I think already millions of reactions take place. Well, from chemists, that is quite complex. And of course, we never can analyze it with our machine. But I would like to highlight 2 reactions what are important with artificial aging. And that is, one is the oxidation step. So the first reaction here, where you get, due to the oxygen and radical formation, you get carboxylic acid formed and low molecular weight. And the second reaction, what is more important is the hydrolysis. So in the presence of water, you get indeed hydrolysis of the ester band here, group here, and you get indeed loose fragments. So the fatty acids are released. The last thing I would like to share with you about the background of this oil paint chemistry is that we do not see oil medium and pigment as two separate things, although they are mixed. There's a lot of interaction. I'm sure you are aware of that. So at the moment they are mixed, the pigment and the binder, you see that as the binding medium is drying, and from the left you see the acid groups formed, but the metals from the pigment or the dry interact with the acid groups that formed, and there you get an ionic network. And that's how we see, between brackets, an mature oil paint as an ionomeric-like system. Okay, let's get back to the artificial aging conditions and jump a little bit into the factors of that influence the aging. Well, I already mentioned it in the initial state with the background of the oil paint drying, and that UV triggers a lot of radical production. And that's also happening here. Your photon, what is released by UV or visible, need to be absorbed by the binder or the pigment. And in the case, if you do light aging with your oil paint, you get an overproduction of radicals and also an overproduction of oxidation. So what we mostly see when you photo-oxidize or light age your oil paint sample, that you get an overproduction or a relatively high amount of small oxidation products like small decarboxylic acid compared to a neutral aged paint sample. Well, it's also good to be aware that there are different sorts of weathering and light aging chambers. You also can build them yourself. It's important to be aware that your lighting is homogeneous, all these type of things. And you need to decision what type of lamp are you using. Do you use xenon lamp, UV light, and LED light? And it's important that every lamp has a different spectral power distribution. Then thermal aging. This, of course, when you put your samples in the oven, and you result in a faster drying and hardening of your oil paint. And if you go into the literature, you see temperature between 50 and 80 degrees, but you also see them above 100 degrees. Under higher condition, the lower molecular weight fractions are faster evaporated. And the temperature also affects the relative amount of the free fatty acids. And these free fatty acids are normally the plasticizers in your paint film. So if you age your paint film under higher temperatures, this can really result in a more brittle and stiff paint film. And it's also important to be aware, so if you age your samples in an oven, and the oven is not humidified, under high temperatures, the water content is lower. So it's also be aware that certain processes cannot take place. Then relative humidity. Well, I already showed you with the reaction of hydrolysis. It has a significant influence on the chemical composition of the paint. Water catalyze the acyl glycerol hydrolysis and lead to the formation of relative high amount of oxidation products and smaller fragments. So actually the network is really breaking down. So yeah, and that also results that your paint can become softer. Well, how to create a relative humidity environment? And there are indeed, as I mentioned, different sorts of weathering and aging chambers for aging, but to get the right relative humidity or fluctuations of that. But you also can build them yourself, as you can see here on the picture, where we use a saturated salt solution and build actually within a box and a mini weathering chamber. And then the last of the 4 topics are listed about critical decision to make. And what do you want to do with them? And when you design your models and reconstruction, you really need to think a step ahead. What kind of analysis can I do and what do I want to perform in the end? And for instance, if you want to study the paint morphology and the surface characterization in an electron microscope, and take care that your sample fits in the chamber in the microscope. Or if you are going to do reflectance infrared and your layer is too thin, be aware that indeed features from the substrate will also end up in your spectrum and will be detected too. And also, I don't know if people are going to synchrotron facilities, also be in discussion with the beam scientists of these facilities. How do I prepare my samples? Because sometimes the sample preparation in synchrotron facilities are quite restrictive or need certain care. We're coming to the end, so I would like to come back to the row or the chain of different models and reconstructions. And I would like to zoom in a little bit to the smart design models. As I said, one of the challenges is that we don't have the time to age our samples 100 years. So we need to think about how we overcome that step. And we also think of a mature oil plant as an ionomeric system, as I showed here on the left, where the metals are integrated in the oil network. So there we have to do a smart synthesis, and I just copied the synthesis from our publication, how we make these systems. So we thought at certain point, can we not synthesize a 50-year-old oil paint to study indeed these ionomeric properties a little bit better? So we added to the oil paint indeed the carboxylate bond, so we are sure these metal carboxylate are in there, so we don't need to wait before they diffuse into the system. And with this type of systems, and you see them here on the right, a model system, that's what I call a model system, and we just do experiment. For instance, we add more fatty acid to see if metal soaps can form. So you can play around to understand certain properties of your mature paint film. Another example we have about smart design models is this system. This is a multi-layered system of 2 layers. And one of the research questions I had, if I apply a solvent on a paint film, do I extract fatty acids from lower layers to the top? So what we made 2 layers, and in the lower layer we added fatty acid C17 as a marker, because C17 is not naturally present in the oil, and a zinc polymer, what I presented in the previous slide, on top. And then we applied with different cleaning methods, a swab, a gel, or a tissue on top, and then it releases, in this case, ethanol, and it absorbs ethanol, and then we analyzed the cleaning method and also made cross-section of these 2 layers. And by tracing down the C17 with mass spectrometry techniques, we could see, having the question indeed, do these techniques or the solvent absorb fatty acids from lower layers and replace them to top layers or extract them? So that are also a way that you can use markers to understand processes and study them. I'm coming to the end of my lecture, and I would like to give more a summary. It's centralized about 2 questions. Why are we using models and reconstruction, and what are useful models? I hope to give you a little bit insight in my chain of thoughts here. Always keep in mind that it is important. So what are your research questions, and how are reconstruction models going to help you? And you have to realize that it's an iterative process. You go from your painting to your model, and for your model to your painting. So you need to make this loop all back. And the last slide I would like to finalize with is what I was discussing with my PhD student Jurien Dijvenvoorde in preparation to this lecture. She said, making the model is already a very valuable process. And I think that is so true. Thinking through, what do you want to know? How are you going to do? What are the chemical and physical processes? How are I going to capture it? So I think going through it is already a valuable process on its own. And with that, I would like to thank you for your attention.
Thank you very much, Catherine, for this wonderful lecture. If you can now...
Yeah, I did.
Thank you.
Can you control it, Fabiana? Not yet, I think. One second.
Not yet. Or you can just move to the next slide if you prefer.
Yeah, I can definitely do this.
While we give time to the audience to ask questions using the Q&A function. Thank you. So I would like to take this chance to show everyone and announce the whole program of the lecture series Current Topics in Heritage Science that we prepared for this year. As you can see, there are 10 lectures by 10 incredible speakers that will go from today up to June in next year. They will happen monthly on the third Thursday of every month. And we hope that you will join us for all of them. You can find more details on the Hyperion website and all the details about the lectures and the registration link for each of them. Catherine, if you could switch again, thank you.
Yeah.
Thank you very much. The next lecture in particular will happen on October 20th at 3 p.m. Rome time, and it will be a lecture by Dr. Vivi Tornari on the principles of holographic interferometry for non-destructive subsurface examination. So we hope to see you on October 20th as well. And thank you very much.